Right, welcome back. Yesterday we were talking about rational functions, and today we're also going to be talking about rational functions. Specifically, we're going to be trying to graph them. So, yeah, in this case, just a little bit of notation first, and then I promise you, we'll do a lot of examples. This notation, okay, again, mostly I like your book, but there are a couple of things they do that kind of drive me a little nuts. And one of them is they use calculus notation in a non-calculus course. So, and it's pre-calculus, but still, this is more of a calculus thing. So they're saying as x goes to negative infinity, okay, then f of x goes to what? You have to look at the graph. So normally in calculus, you're going to see this as a limit as x goes to negative infinity of f of x. So this is coming. But this whole idea of like x pointing an arrow to this is as x tends towards negative infinity, or as x grows without bound in a negative direction. Okay. So I like the either tends towards infinities or grows to negative infinity. I don't like approaches negative infinity, but that's usually what you're going to see it as in calculus books. And there's no reason why that has to happen. But as we're tracing this toward negative infinity, right, we're getting more and more and more negative here. It looks like this function is getting closer and closer and closer to 2. Okay, so f of x would be 2. That's what they're wanting to have for an answer here. No, they really, we got to press the little button, huh? All right. Another thing I'm never going to get ready to. Or okay, as x goes from 3 to the left, okay, so as x is going, that's what this means. Okay, so as x goes to 3 from the left, what is x? So this is as x approaches 3 from the left. Okay. So we're going 3 coming down here, and it looks like we're going to negative infinity again here. So this we're not again, but we're going to there. All right. So we're happy there. As x goes to 3 from the right. Okay, so again, this is mostly just notation stuff. And since it's new, it's going to take you a little bit longer to kind of sift through this than it would take somebody who's been used to seeing it for a while. So I'm sure after you get done maybe 2 problems, you're going to be a pro at this. Okay, so it's going from 3 to the right. So it looks like a positive infinity there. All right. And the last one is just, this is like the same as the first one, right? This was, okay. And usually in calculus, technically these things are undefined because they're not numbers. And if you're going to have this going here, you're going to have a number. But there's a special case for positive and negative infinity like this, because saying it doesn't exist is one thing, but saying it's tending toward one of these two, infinity or negative infinity, gives you an idea of the behavior of the function near that point. So that's why we make the exception to show you that, or to say that, even though technically we're going to be saying does not exist. Okay. So we're going to have as x approaches infinity, f of x. And again, we're just looking at this on the graph and saying, oh, looks like we're getting to 2 there. Okay. Equals 2. We'll go back to here. 2. 10 parts. Oh my goodness. Okay, increasing or decreasing, right? So increasing, decreasing. So it's decreasing, right? This, if you go skiing at all, right? The decreasing part is the fun part of skiing. Okay, the increasing is the not so fun part of skiing. Unless you're a real big cross-country snow guy or snow person, then you'll be increasing. That'll be fun for you. But for most people, this is not the fun part. Okay. And you always have to write this right from left to right. So as we're doing this, right, this would be the fun part of skiing here. This is probably not so fun, but it's still technically the fun part of skiing, right? So this would be a decreasing function. And when you look at this, it's very tempting to look at this value and say, oh, it's going up. Like, no, we have to read it from left to right. So it's actually a decreasing function always, okay? If I put you on skis on this function, and you couldn't die, okay? You couldn't descend into oblivion, then this would be the fun part of skiing all the time. So this is always a decreasing function, even though we have a discontinuity in it. Okay, so it is always decreasing, except for, right, except for it's not defined. So it is decreasing over, the graph is decreasing over at least one interval, yes. It is never an increasing function. All right. So that's just how to think about it. I know it's very tempting to look at the arrows and look at and what you think the arrows are doing, but you always have to go back and remember we're going from left to right. Okay, that's the big trick with all of this. So interval notation up to where's our graph? Up to 3. Okay. And I just put out a little mini guide to interval notation because I know that people have asked. So I put out a little one in your class. You should see a focused topics type of a thing. It's 10 minutes, so you don't have to listen to me that long for that one. Even that's probably too long. Okay, so there we go for intervals. It's always decreasing, except for, again, at 3. The domain in interval notation, and that's another thing. As I wish we were still face-to-face, because I always tell my students there's another way to do this, right? We could do interval notation as negative infinity up to 3, union with 3 up to infinity, but it's all the numbers except, so this is all the numbers except 3. Right? That used to be the way we would write this stuff. And you still might in other classes, but they don't give you the option in this one. They just say you have to do it this way. So be it. There we go. And it's good to practice the interval notation. And this is about the level. This is about the point at which I start to insist that you guys start actually doing this. But if you were one class back, right, if you were still in college algebra or in intermediate algebra, and you wrote this for me in English, I think that's a great answer because it shows that you've internalized what the heck is going on. And even though at this point in your career, your scholastic career, you'd like somebody to start writing it in interval notation all the time because that's what's going to be expected from you, this also, I mean, sometimes people guess this, but they don't really know what it means. This one, I know exactly what you meant. Okay, so that's always a nice answer. But at this point, we start docking you for writing this instead of, the proper way of writing it. Okay, the range. Okay, I always hate asking about range unless you have a graph. So what's all the y values, right? The range is all the y values except for, well, there's all the legal values of y. And it looks like it never actually gets to 2. Okay, now you can't be 100% sure because, like I said, these functions can cross a horizontal asymptote, but I'm gonna guess that if they had one of those weird features, that they would have showed it on the graph. Okay, so because this doesn't actually intersect 2 at all, we're gonna take them at their word, and we're gonna say it goes from negative infinity. Oops, oh, they just have a whole negative infinity there. We're set up to 2, and then we're going to skip over 2, and then we're going to go from 2, that means that includes, all the way to the highest part. Okay. We have a vertical asymptote, right, at x equals 3, I believe. X equals 3, we have a vertical asymptote. Right. And a horizontal asymptote at the line y equals 2. All right. Not too bad. Boy, it's a long problem. All right. So that just kind of clears up, I think, all of the extra little miscellaneous odds and ends that we have, and really what I'd rather do is kind of run into like graphing some of these things. I think the rest of these problems are going to be very similar. It's just good. You need the practice. All right. Do we have to graph this thing? No. I don't want to do that unless we have to graph it. Sorry about that. All right, there we go. Nice graph. Okay, so this graph. Okay, for vertical. Okay, so let's go ahead and plot all the necessary asymptotes, and then we'll kind of go through all of this. So, do we have any common factors? There's nothing I can factor here. There's nothing that cancels. We're just kind of done. So no common factors. Okay, but to be honest, this even in your book, even at this class, this is kind of rare. But you should always get in the habit of checking it because they can surprise you once in a while. And now we're going to check out what's our vertical asymptote. Well, remember, the vertical asymptote is when you set the denominator equal to 0 and solve. So we're going to say this is 2x plus 7 equals 0. 2x is equal to negative 7, so x is equal to negative 7 halves. Okay, so that's our vertical asymptote. What about a horizontal asymptote? Well, there's 4 conditions, remember? And they all have to do with the degrees. Well, the degree of the top here, right? The degree of the numerator is 0. It doesn't have any x's in it, so that degree is 0. The degree of the bottom, the degree of the denominator, right? Degree of q of x, that's the bottom, is 1, right? P of x over q of x is the standard way of writing this stuff. So since the top degree is smaller than the bottom degree, we have case 1, like we talked about yesterday. And that's going to be, we're going to have horizontal asymptote at the line, y is equal to 0. Okay? And at least 2 points on each side. So let's go ahead and just put our asymptotes in so we can kind of see what we're working with. So we've got a horizontal asymptote at 0, and we've got a vertical asymptote at, what was it, negative 7 halves. So that's like 3.5, right? Negative 7 halves. Okay, so there's our skeleton that we're going to hang our function on here. All right. So we need 2 points on either side. Okay. So pick your 2 favorite numbers that happen to be smaller than negative 7 halves. Okay. And in face-to-face, I am more than happy to let you guys come up with any number you want. Okay. So you guys usually, I let you guys tell me, how about we look at x equals negative 5 and x equals negative 8. All right. I noticed that there's a 5 and an 8 on here. You could have picked any other one you wanted to. You could have picked, if you wanted to pick, what do we have, 3 halves here, so it's close to 4. If you wanted to pick x equals the negative square root of 17, you'd be my guest, all right? Because it's a little bit close to 4. I'm not responsible for your arithmetic at that point, okay? So negative 6, and then we have 2, negative 5, plus 7. So it's negative 6, negative 10, plus 7. That's going to be what, right? Negative 10 and 7 is going to be a negative 3, right? So negative 6 over negative 3, that's 2. So when x is 5, x is negative 5, n is 2. Okay. How about 8? I didn't know. All right, I just picked two numbers that I thought anybody else would be unlikely to pick. All right, so the next one, we're just going to plug this stuff in. So we have negative 6, negative 16 plus 7. So we have negative 6 over 16 and 7. 16 minus 7, that's 9, right? So, yeah, so that's going to be cast out the 3's, and that's going to be 2/3, it looks like. All right. So we have negative 5. So let's see here. Let's use their different tools here. We have negative 5, 2, right? And then the second one, I don't want to graph 2/3 on this graph. They won't let me anyway. So what we're going to do is we're just going to plot the point. We're going to say this is negative 8, right? Negative 2/3. Okay. Actually, I would not have recommended doing square root of 17 because you'd have square roots in here, and I won't let you do it. All right, so that's 2 points in this region. Wait a minute, that's not right. Let's erase that. Should have been positive 2/3, right? So this is negative 8. And then 2/3. There, that's better. Okay, well, what about over here? Okay, pick your two favorite numbers that happen to be greater than negative 7/2. How about 0 and 1? Okay, those are two good points. Those are points you probably would have picked. Okay, so we have negative 6. We have 2 times 0 plus 7. So this is negative 6/7. All right. For x equals 1, we have negative 6. 2 times 1 plus 7, right? So we have negative 6. 2 times 1 would be 2. 2 plus 7 would be 9. So it's negative 2/3. Okay. So let's see here. We have neither one of these I can plot. I'm going to have to use the tool for both of these. Okay. So we plotted the points. So notice I hit plot point and it reset it for me. So here we have 0 and negative 6/7. So it was very good about doing that for me. Plot point. And then we have 1. And now we have negative 2/3. All right, so again, give that to me very nicely. So we go back and we have our piece here. Oh, wow, they were really, usually you had to draw this and connect the little dots here and put it in here. They streamline that a bit, I guess. That's nice. And check answer, and then we're good. All right. So let me ask you one more question about this. See, there's a lot of follow-ups. How do I know if f of x, or if n of x in this case, crosses its asymptote? And if it does, where? So what we're going to do is we're going to set this thing equal to the asymptote, right? We're going to set n of x equal to the horizontal asymptote. That's a y value, right? This was y equals 0. That's how I'm getting this. Okay, y was equal to 0. So we're just going to say, well, this was negative 6 over 2x plus 7. Set it equal to 0, and now we're just going to solve. Okay, so if I had x's up here, then we'd probably see something. But in this case, you know, how do you solve a rational equation? You clear the fractions. You make it not a rational equation. That's the first thing you do. So that cancels. 2x plus 7 times 0. We just get negative 6 is equal to 0. Well, that doesn't work, right? That's never true. So since I know that this never happens, I know it never crosses the asymptote. Okay, that's how you tell. All right, let's see. We'll do this one. Okay. Let's talk about something else too. Okay. So for this one, right, we have, why does it end still? We have 6 over x squared minus 9. Okay. So again, do we have any common factors? No, no common factors. What are my vertical asymptotes? So we set the bottom, set the denominator. X squared minus 9 is equal to 0. X plus 3, x minus 3 equals 0. And then we're going to have x is equal to negative 3 or x is equal to positive 3. So the line, right, x equals negative 3, the line x equals positive 3, those are our vertical asymptotes. Okay, remember, x equals something, that's a vertical line, right? How about our horizontal asymptote? Well, we have 6 over x squared minus 9. The degree of the top, right, the degree of the numerator, that was 0. The degree of the denominator, I shouldn't do this notation. It means something else in calculus, so I should probably just write this out. I don't have a good notation to say the degree of this polynomial. I'm sure somebody has it somewhere, but if you write d next to a number, that means something in calculus. And capital D, there's some older books that still use that. Most of them use little d now. Right, the bottom one is smaller than the top. The top one is smaller than the bottom. So we still have horizontal asymptote at the line y is equal to 0. Okay, just like the last one. Okay. And now they're going to have us graph some things in each of the different pieces here. So let's go ahead and lay out the skeleton here, and then we'll see. So we've got that one. We got that one, and we have that one. Okay. So we need points in each of these intervals. Okay. So let's pick our favorite points in between positive 3 and negative 3. Okay. And this is where it starts getting tedious here. So how about we pick x equals 0? All right. Well, 6 over 0 squared minus 9. So that's 6 over negative 9, which is negative 2/3. Okay, and because I see the net they cast on this thing, I'm going to have to use the tool to graph that thing. Pick your next favorite point between 0 and 2/3. Right? And so that's going to be or 0 and or between negative 3 and positive 3. What am I thinking? Let's pick 1. So this is 6, 1 squared minus 9. That's 6 over 8, negative 8, which I believe is negative 3/4. Okay. Let me try something, because just because I know, right, just because I know that these are both negative, right, we've got 2 points. We've got 0, 2/3, negative 2/3 rather. 0, negative 2/3. And we have 1 and negative 3/4. All right. Now, how do I know that this graph is going to do this? What's going to happen on the other side here? Is it going to go down there? Or maybe it comes up? Okay, well, the first thing we could do is we could check to see whether or not it crosses the asymptote. Does it cross? So 6 over x squared minus 9 is equal to 0. Same deal, right? We're going to multiply both sides by the denominator, and we're going to end up with the result 6 equals 0 and say, well, it never happens. So it does not cross. Okay. The other thing we could do is we could check for symmetry. Okay, so back in college algebra, You probably learned about even functions and odd functions. We plug in negative x there and we see what happens, right? So we know that if f of negative x looks like you factored out, you didn't, okay, but it looks like you factored out the negative sign, then you know this is an odd function. Right? If f of negative x is equal to f of x, then we have an even function. So odd functions have the property of whatever goes on up here is going on down there. Okay, pretend that these are the same. Okay. Even functions is kind of like looking in a mirror. If you have something over here, you got something over there. Okay, you got the same thing. Okay, so let's check. We've got what, 6 over x squared minus 9. This is equal to f of x. What if I try f of negative x? What's that? Right, everywhere we see an x, we're going to replace it with negative x. When we simplify this, I got the same thing. So I know this is an even function. So whatever happens over here also happens over there. What does that mean for my the amount of work I have to do, right, for this region? Well, I don't need to type it into the computer. I don't need to reevaluate the function. I can just pick a point over here, and you know it's mirrored on this side. Okay, so let's try. Pick your favorite number that's bigger than 3. How about x equals 4? And how about we do it x equals 6? Okay. So we have, this is 6, this is 4 squared minus 9, so this is 6 over 16 minus 9, and I believe that's going to give us a 6/7. But I also know, at this point, because it's even, that if x is equal to negative 4, that's what this is saying. If f of x equals something, then f of negative x will equal the same thing. Then we're also going to have f of x equals 6/7. Okay, that's what even functions are doing for you. So the positive thing equals one part, the negative one equals that same thing. Okay, and then we have 6 over 6 squared minus 9. So that's 6 over, what's 6 squared is 36 minus 9. I believe that is going to give us 6 over 27. 27 and 9 makes that. We can cast out a 3 here, so what do we have? We have 2 over 9, I believe. Okay, and I also know that when x equals negative 6, y is equal to 2/9, assuming I did this arithmetic correctly. Right? So let's go ahead and plug in. We got 4 points to plug in here, right? So we have 4. Of course, I wasn't going to remember that. 4 and 6/7. That point. And then we have 6 and 2/9. Okay. We also have negative 4, right? And 6/7. Oops, not plus. Get out of here with that. 7ths. Right. Puts it over there. You can see mirror image. And then we also have, what was it, 6 and, oops, negative 6. And 2/9. All right. So we're good. And then we're just going to go ahead. Wow, they did. They made it so much nicer. Usually you have to fit these things over your points. But that's how I'm going to say that's what I'm going to say my answer is. I still try to teach this as if you were doing it all by hand because, that's how I did it. And I don't appreciate the 21st century yet. But the other thing is that, later on when you get to calculus and you have to draw something, like you're not going to have a nice tool like this. You're just going to have to draw it. So, it's good to get the practice to do that too. All right. So let's see. What do we have here? Okay. Okay. Well, want to do one that's going to be a little bit more interesting. This one isn't, but since I often ask this one, there's one that's very close to this on an exam. Like if I have to pick one, this is one of the ones I'm going to pick. Okay? And you'll see why is because it doesn't have, it still has all the parts, but a lot of the parts are pretty simple to figure out. All right, so here's my function. So 1, do we have common factors? I promise you on Monday we will do one that has a common factor, okay? But since this didn't cancel, okay, there's none, okay? And remember, that's when you have a whole rather than an asymptote, okay? But we checked. And again, we'll go over one definitely on Monday that has one. What's my vertical asymptote? 3x minus 7, set that equal to 0. Take the bottom equal to 0. And then go ahead and solve this. That looks like a delightful vertical asymptote. What about horizontal asymptote? Okay, well, the top, right, is 5x minus 1. The bottom is 3x minus 7. Since the degree of the top and the bottom are the same, we use DEG. That sounds like a good thing. So that'll be the degree of Q of x. And they're both equal to 1. All right, they're both equal to 1. So they're the same. What was the rule when they were the same? Well, we take horizontal asymptote equals the ratio of their leading coefficients. Right? It's the ratio of their leading coefficients. So the line y is equal to 5/3, right, is our horizontal asymptote. Right? And then 4, we're going to plot some points here. Okay, this is the tedious part of it. All right, so what do we have here? We have really, you know, I don't know if they'll let me do that, but vertical asymptote, 7/3. Well, where the heck is 7/3? Oh, it's a little bit bigger than 6/3, isn't it? 7/3 is a little bit bigger than 6/3, and 6/3 I know is 2. So this is a third past 2. That'd be 3. That's too much. I get the right number? I did. I wonder if they'll let me do it this. No, that's a point. They don't want to do that. Oh, please fill in. I don't want to fill in the empty boxes. Let me go. Oh, wow. Okay. Let's just put something in here, and we'll say 0, 0, even though I know it's not true. We'll say plot the point so I can get. Wait, what? I'm not used to a laptop yet. Can I get away from this? Usually, there's a way of not dealing with this anymore. You can usually have an X over here. I think that's happened like every time. And now it's covered by this stupid tool. Yeah, okay, thank you. It's wrong. Thank you very much. All right, it didn't like that, so we're just going to have to estimate this thing. We'll call it that. It's the best I could do. Okay, and hope that it fills in the blank for me. My vertical asymptote was 5/3, which was right, 5/3, not quite as much as 6/3. It'll be a little under 1. So we're going to do that, and again, hope for the best. So there we go. And now I guess I hit this twice. So now we have to plot some points. So here we go. Pick, right, your favorite point that is smaller than, right, 7/3. How about 0 and -2? So let's pick 0 and -2. All right. So we have 5 times 0 minus 1, 3 times 0 minus 7. Well, that's -1 over -7, which is 1/7. Okay, so we have the 0.0 1/7. Okay, pick -2. So we have 5 times -2 minus 1, 3 times -2, 3 times -2 minus 7. All right, so what is this going to do for us? We have -10 minus 1, -6 minus 7. So what is this going to do? This is going to be 11, right, over 13. These are both negative, so they cancel. So we have -2 and 11/13. All right. I'm sure those are both delightful numbers. All right, so we have 0 1/7, 0 1/7. Oh, did it keep that on me? It did. I wonder if I could do this. Let's see if I can. Nope. All right. Well, let's keep going then. It'll yell at me because I'm not correct. So I didn't erase that point. So it's going to get upset with me. All right. All right. And we need 2 on the other side, right? Pick 2 of your favorite numbers that happen to be bigger than 7/3 here. All right. How about 4 and 6? We're just going to go through the same thing here. Okay. So 5 times 4 minus 1 over 3 times 4 minus 7. So we have 20 minus 1. We have 12 minus 7. Yeah, that's okay. So we have 19 fifths. Okay. So we have 4, 19 over 5. If I pick 6, 5 times 6 minus 1, 3 times 6 minus 7. All right. So that's going to give me 30 minus 1 and 18 minus 7. Yeah. So what are we going to have here? We're going to have 29 elevenths. Crazy numbers. Fortunately, we don't have to keep track of a lot of that. All right. Let me ask you one question now. Does this function cross its asymptote? Okay. So for something to cross the asymptote, you gotta have to have some weird stuff going on with the top, depending on the bottom's not going to matter so much, but you're going to have some kind of weird. So by inspection, I would say no, it does not. But that's only because I had the luxury of doing a couple of dozen of these before. Let's check. Okay, so we have, what is this? 5x minus 1, 3x minus 7. What was our asymptote? It was 5/3. Okay, so when I multiply both sides, right, a little bit harder now. Okay, one side doesn't just be 0. We have 5x minus 1 is equal to 5/3 times 3x minus 7. See what happens here? So we have 5x minus 1 is equal to, this cancels, 5x minus, we'll say 35/3. And then these guys cancel, and you're left asking yourself, is -1 equal to -35/3? And clearly that is no. That's not true. So this thing never crosses its asymptote, so we don't have to worry about that. All right, so it's gonna fail me on this one because I forgot to erase a point, and I can't get back to that tool. So there we go. All right, this is 29/12. Oh, it even covered up the whole little thing that I could use to, yeah. What a crummy problem set up here. Maybe it's on this side. No, it's nowhere. All right, well, guess what? You're wrong, of course. All right, so we know why. We forgot to erase that point, and we didn't have a chance to do this. So, oh well. We'll move on from there. Actually, we might say we could stop there, and next time, let's look at something that. Excuse me. Oops. Sorry about that. See, I think this one has a hole. One of the last ones had a hole in it. So we'll make sure we do that so that you can see what happens with that. Okay. So we'll go ahead and stop us there. I'll make sure we do a couple of the last ones next time. It looks like we got done about 3 of these today, plus a lot of talking. So I have a feeling we can do 14, 15, and 16 on Monday and say that we've covered rational functions at that point. Okay, so we'll hit the last 3 of this section next time, and we'll call it a day there. All right. So I'm going to go ahead and stop recording.